Okay, good afternoon, everybody. I do apologize for how warm it is in here. I seem to have no control over that, so I'm sorry. We do have water outside. It's pretty cold, so you feel free to hop out if it gets really hot. My name is Bruce Momjian. I am one of the Postgres core team members, and I work for a company called Enterprise DB. The goal of this talk is not specifically Postgres, but really to talk about the idea of database hardware and some of the unique things that are necessary when you're basically purchasing or configuring a database server. And it's quite a bit different than the things you would normally worry about if you were configuring a web server or something else. So basically during this period, I want to kind of highlight the differences, highlight some of the things you have to look at, and I think you'll find that there's some very simple things that can be done, which make a huge difference in your database capabilities for a server. Again, I am a Postgres core team member, so I'm going to talk about Postgres a little bit as I go, but again, these concepts are not unique to Postgres. Oracle, MySQL, DB2, Microsoft SQL Server all have the same kind of requirements. They handle them slightly differently. I might go into that a little bit if there are questions about it, but in general, there are some pretty constant things that you have to worry about. Even Informix uses the same kind of idea. I will take questions as I go, so that interaction and so forth. So I'm used to that. I was a high school teacher, so if it feels like you're in a high school class, then I guess there you are. One funny thing before we get started, I was looking at the schedule to find out what I was going to miss when I was speaking, and the one that really stuck out was there is a talk that has Star Trek in the title, and I'm like, oh my goodness, I am up against Star Trek. But then I looked at the full title, and they mentioned Star Wars, and I was like, okay, I'm okay, So I don't know if you're Star Trek or Star Wars fans. That is a age-old argument, but I can say that I went to a Star Trek convention when I was 12 years old, I think, or maybe I was 14 in New York City. So that's usually what I have a tendency to root for. So anyway, when I saw a Star Trek talk, I was like, it's not a Star Trek talk; it just mentions Star Trek in the title. So, any questions before we get started? Great. Okay. So, what are we going to talk about today? Are we going to talk about CPUs? Are we going to talk about gigahertz? Are we going to talk about NUMA and SMP CPU stuff? No. We're going to talk maybe a little bit about it, but this is not what we are going to focus on. And you might think that's like crazy, but I'm going to explain why I don't think it's crazy. Particularly when you're talking about a database server, and I hope by the end you'll actually agree with me. If you don't, you can tell me that you don't agree. Okay, so this is the image that I want you to remember from this talk, although the one I want you to remember looks slightly different than this one. But what I've done is I've taken the three aspects of a server, in general, and I've made a pyramid out of it. Top, I have the CPU because that's mentally the way I think of the server. Probably everyone has the same thing. It's sort of the control brain of the whole thing. Then underneath that is the memory, where you basically decide where am I going to store stuff, and it helps the CPU. And then at the bottom you have I/O. And if you look at the relative sizes of these things, this is kind of the way people think about it. And I had to basically, for database workloads, I had to basically retrain my brain not to think this way. Because if you look how small that I/O thing is at the bottom, right? It's just this little triangle kind of right there. Well, actually, I should do this so you can see it on the other screen. But this triangle, it's just like a little thing. And everyone normally, when they're thinking of I/O, they're thinking, oh, my stuff's stored on disk. Okay, I'm done. Like, that's about and I'm not going to run out of space. So those are the two things. Did I hit the save button? Okay, it's done. I'm done. And how much free space do I have? Okay, I'm good. And that's about, for general database, general server use, or general, certainly consumer use, That's about as far as it goes. Okay? And I'm here to tell you today that that is not the way you should think about a server if you're configuring it for a database. And I'm going to specifically explain why that's true, and I'm going to go into specific cases of exactly what things you should be looking for, why I think those are important, and I think you'll come out with a better understanding of database hardware selection. So this is what I want you to think of. Okay, this is the slide you want to remember. The CPU is now the little triangle at the top. Okay, it looks really small, but honestly, for databases, it is really small. I'm going to explain in a minute why, but that's not usually a thing you have to worry about. Now, there are some workloads, where the CPU is really important, but relative to the other parts, it's really not that important. Okay, so I realize it looks small, but you got to realize that the I/O is big. Okay, and the memory is also somewhat big, and the CPU is this little thing at the top. Okay, and that's sort of the retraining that I think we should do when we're thinking about databases. And again, this presentation is not all pretty pictures. We're going to go into some real detail here. So, why the difference? Why am I telling you that you have to rethink how you think about servers? And frankly, this model that we think of here, we all grew up and had computers when we were kids, or we'd play games on them and do what. This is how you think of, like, when you're playing a computer game. This is kind of how you think of your server, right? But we're not playing computer games. We're actually running a database. And again, it's not surprising that, in fact, there is a different way of sort of looking at it. So frankly, when people send requests to the Postgres email list, and they say, here's a server, is this good for Postgres? And I'm sure other databases have the same issue. They'll tell us, oh, it has this many CPUs, and they're this fast, and I have this much memory. And when they talk about I/O, they'll say, oh, I have 2 disk drives, and maybe I'm going to mirror them. Or, this very sort of perfunctory, oh, by the way, I have some I/O as well. I store things too. And again, it's just really not a great thing. So why the difference? First thing is the traditional servers have that CPU focus because they're normally dealing with things like network overhead, HTTP, processing PHP, processing Java stuff, processing email, running virtual machines. These are very CPU-intensive processes, and application code, which is obviously very CPU-intensive. Okay, so when you're doing a traditional server, not surprising, CPU is very important. But databases really don't have the same requirements as a typical application. What databases do uniquely are things like sequential scans of huge numbers of tables, right? Like sequential scans of a huge table. Normally, applications don't do that, right? Games don't do that. You don't do that when you're processing email. But we do this all the time when we're doing a database. So all of a sudden, you can see the emphasis on the need for a strong I/O channel because you're doing something unique in a database that you typically would not be doing in another system. Index scans, causing a lot of random I/O. Again, I can't think of another application that does random I/O as much as a database. Pretty much everything for normal applications, open the file, write it, and close it, right? Just throw it to the drive. But databases, they're scanning around all sorts of things, pulling stuff off indexes. Again, very, very I/O intensive. Unpredictable query requirements. Very few systems have a language where you basically say, oh, by the way, go give me every product that I sold between 1 p.m. and 2 p.m. yesterday. And all of a sudden, the system's supposed to go, oh, okay, I will go and sequentially scan all these tables and do all these index lookups, and I'll have an answer for you within 10 seconds or something like that. That's just not typical for an application. Normal application access patterns are very predictable. They sort of take a batch of job work in and they process it and they spit it out again. Database is not that way. You're reprogramming it. You're re-requesting things that are unpredictable all the time. Reporting, again, huge I/O requirements. You're spinning through huge amounts of data. And again, these do not require a lot of CPU. In most of these cases are going to be I/O constrained. So this is a Postgres-specific slide. I think it's the most Postgres-specific slide I have. And I'm just going to highlight a couple things about Postgres. And this is going to translate. I know I see a MySQL person here. I'm sure we have a couple Oracle folks here who know a lot. So feel free to kind of chime in as we go through this. But I just want to cover a couple things about the architecture of Postgres. Again, similar to other databases. The two things are really on one side. On the left here, we have the Postgres shared buffer cache, which is where all the in and out, all the I/O is, all the sort of reading and writing of data is happening. And then underneath it, we have a kernel, and underneath it, we have the disk blocks. Okay, so in Postgres, we actually have two buffers here between the actual shared buffers and the actual disk blocks. So effectively, if you need to read something, it's got to be read up from the disk blocks to the kernel, from the kernel into the shared buffer cache. When you modify some data, eventually it has to be written down to the kernel and down to the disk. Okay, so there's a lot of I/O requirements here. On the right-hand side, we have the write-ahead log. Now, again, this is unique to Postgres only in its name. Other systems have very similar concepts for databases where you have some type of commit log, some type of transaction log. And the interesting thing about the write-ahead log is that it's got to be pushed to durable storage. Because Postgres being a relational database, you have to have ACID compliance. You have to have what we call durability. That means that if you commit a transaction and you lose power, we assume that that data is safely stored. And the only way we can safely store it is for the write-ahead log to be on some kind of permanent storage. Now, in this very trivial case, effectively you have to write the write-ahead log to the kernel, and then the kernel has to write it directly to the disk blocks. Now, you can use direct I/O and a couple other tricks here, but effectively you're having to write your write-ahead log down to some kind of storable storage. Okay. Now, if your durable storage here is magnetic disk, you got to wait for the the platter to come around, and there's a whole bunch of complexity there. In fact, I'm going to break out that stack here. So here we have the shared buffer cache. Here we have the write-ahead log, and down here, this is a breakout showing you magnetic disk. Okay, and you can see that when the write-ahead log needs to write something, it's going to write it to the kernel. The kernel being in RAM is obviously not durable, so the kernel has to write it out to the what we call the host bus adapter or some kind of drive controller, storage controller, and that may have a cache in it, and then that has to write it to the disk cache. And then if that isn't durable as well, it has to write it to the magnetic disk. We have to wait for the head to come around. We have to wait to get it on the magnetic surface. And only then can we do effectively an acknowledgement of the write, which then goes up to the disk cache, back to the controller card, back to the kernel, up to the write-ahead log, and finally we've committed our transaction. Now, if you're familiar with how slow magnetic disks are, and again, many of you may not be using magnetic disks anymore, but I'm using that as a reference point. Effectively, so the fastest magnetic disk that's maybe spinning at 7,500 RPM or maybe 10,000 RPM if you're really lucky, it's going to do about maybe 300 writes a second, 300 forces of that data to disk. So effectively, no matter how fast all that stuff, how many CPUs you have and how much memory you have, effectively, if you're having to wait for the data to get all the way down and wait for that magnetic platter to spin around, you're going to be, you're going to be doing about 250. I think it's a 15,000 RPM drive. Its max F-sync is 250 writes a second. Okay, that's really bad. That is really, really going to seriously throttle your system. So it doesn't matter how fancy everything is above it. We got to get the data to permanent storage somehow. Now, we do have some disk cache. But if there's no battery on the disk cache, then effectively we lose power, we lose the transaction. Okay? So, in fact, when you set up the system, you have to find out if there's a battery here. And if there's not a battery here, you actually have to go into your etc HDPARM file, at least on Linux, and you actually have to mark that that drive has to be what we call write through. which means you have to write through the cache to the storage, to the permanent storage, and then only then will you get acknowledgement. If it's marked as write back, which many drives are, effectively you're risking loss of data. So if you've ever had a case on a database where you lose power and then the database doesn't come back right, or you lost some transactions, effectively odds are your storage subsystem is not configured properly because you haven't told it which storage devices are actually durable, have durable caches, and which ones don't. Okay. Now I'm going to talk in a minute about SSDs and Fusion IO and all this stuff, but I'm just focusing now on the most traditional case, and that is the case for magnetic drives. Are there any questions so far?
Do you have a preference on write back and write through on disk cache and controller cache?
So the question is, do I have a preference on write back or write through for the disk cache or the controller cache? And I actually have a slide. Okay. You have not seen this before. I don't know you, right? We haven't prepared this. Yes, this is all brand new. So one of the ways you can get a really great boost in performance without having to change all of your storage drives is to add something called a BBU. I know it's a very cryptic term, battery backed unit. I don't know why it's called BBU, but that's what they call it. And you add it to your controller card, to your drive controller card. And what that allows you to do is that effectively when you're writing that write-ahead log down to the kernel, and the kernel sending it to the drive controller call, what we call the HBA, host bus adapter is the technical term. That host bus adapter, because it has a battery, can say, I have durably stored that data. I am done. Here, go continue, and I finished the job. Okay? So what that battery, and that battery may be, I don't know, $100, $300. That's changed our F-sync speed from 250 a second to like 2,500 a second or 10,000 a second. Okay? So all of a sudden it's like you're going from night to day just with a couple $100 battery. Really to the point where, and I hate to kind of beat on vendors, but a lot of vendors and a lot of people just don't understand how important that battery is unless they really work with databases. And in fact, I wrote this talk because I from the email list, Postgres email list, I could tell that people really weren't all getting this. And I needed something that I could show them. And I said, here, show this to the person who is speccing out your server and tell them this is why I need this thing. This is why I need that battery. Okay? Because a lot of vendors and a lot of hardware manufacturers, because they're speccing out for generic servers or for game workstations, I don't know what they're thinking, but unless they know it's for a database, the whole concept of putting, a lot of memory in the host bus adapter or putting a battery in there is like, whoa, like I'm from space, right? Why would I need that? Because again, they haven't really understood some of the unique requirements that databases have to allow for that storage. Now I'm going to go into some specifics in a minute and show you some examples of what the battery actually looks like. Just to give you like a real kind of far. And then we're going to go into SSDs and so forth. Any questions so far? Any questions about how other databases might deal with this? Yes, ma'am. So what happens if the battery fails? I'm actually going to cover that in a couple slides. It is a problem, yes. Yeah, although the newer systems are actually using capacitors instead of batteries, and therefore the batteries don't fail as much. Yep. Other questions? So the question is, if you are adding the battery to the controller, is there anything you have to do in Postgres or anything you have to tell the system? What actually happens, and I'll cover this a little later where I have a particular slide, but effectively what happens is that the controller automatically identifies the battery. So you can buy it with and without battery, basically, some controllers. But as soon as the battery is there, the firmware understands it, and then you effectively go into the controller card, the HBA, and you tell it, you make sure, yes, I have a battery, and then you also have to tell it that when you write to the magnetic disks, they need to turn off the cache. They have to do a write through the cache. They have to write down through the cache instead of doing a write back on the cache, at which point you're defeating the whole problem. Okay? So the problem traditionally, and this is a very weird problem, but normally when people buy consumer drives, those caches are write back, meaning they're not durable. And then all of a sudden you use them for databases, and you have corruption. So I'm going to go into that in a little more detail as I get farther down. Other questions? Okay. So let's go to the next one. This is the SSD one. Okay. This is kind of cool. These SSDs have been around for quite a while. When they first came out, everyone thought, oh, this is going to completely revolutionize the way databases are designed and all these huge amounts of changes that are going to happen. What has happened effectively is it's given us a lot better way of storing stuff durably, and I'm going to go specifically into that. What hasn't changed is that effectively the system still does pretty much the same thing. There are some particular things I'll tell you later about Postgres you can do for SSDs, but in general, it's just another storage, but a lot faster and a lot more durable. Because effectively, when I was working, I've been with Postgres, I guess, for 19 years now, and when I started, the big problem was that there was no really industry-grade way to durably store a small amount of data. Every time you commit, you want to store that data durably. Now, when the battery-backed thing came along, all of a sudden we had a solution to that. SSDs kind of give us an even better solution because effectively any SSD that is useful for databases should already have a battery on it. There are a lot of the early SSDs did not have batteries, and effectively that caused corruption for databases. So effectively, any SSD you buy for a database must have some type of supercapacitor, capacitor. I don't even think they have batteries on them. I think it's basically a capacitor, supercapacitor. And if the documentation doesn't say anything about it, then it isn't there. And I've even heard people say, I will not put it in my system unless I can physically see that capacitor in the device somewhere. I have not actually looked at mine, but I'm sure it's there because people tell me it's there. But I'm going to talk a little later. This staging area that's used for the SSD is much different and much more important than the cache that you would normally have for a drive. So the disk cache here is sort of an optional thing just for performance. The cache for an SSD is absolutely imperative. You cannot write through that cache. You will burn out your NAND, the flash very quickly. So normally you cannot turn that cache off. You cannot force it to go through there, and I'm going to explain why in a couple minutes. But effectively, that cache has to have a battery because you can't turn it off, or your performance will stink, or you'll burn it out, or just don't even try. Okay. But if you're using consumer-grade SSDs that don't have a battery, it's in many ways I would say that's more dangerous than using a magnetic drive with no battery, because at least with a magnetic drive you can tell the operating system use a write through to that device, but on an SSD you can't turn that off. Okay, so again, a lot of hype, a lot of excitement when SSDs came out, but now for the database world, we basically whittled it down to the SSDs that have batteries, have supercapacitors. Good. The SSDs that don't have supercapacitors, great for my son's gaming machine. Okay, that's about all you're going to use it for. You would not want to put that in any kind of production use. And finally, any questions about that? Okay. And finally, DRAM storage. This is best. Fusion IO is probably the best version of that. Somebody today asked me about Fusion IO. So in this case, instead of having flash memory at the bottom, you have effectively DRAM, which always has a battery, because if it didn't have a battery, it would go away when you shut it off. So effectively, you always have a battery. This is obviously super fast, even faster than flash. Again, you can or not have a battery on the controller card. I would say that the battery on the controller card is not as critical when you have the battery on the storage devices. Doesn't hurt. You can get some additional throughput by not having to write it down. But again, you have to have a battery. Effectively, you have to have a battery at the storage layer for SSDs or DRAM type of storage, Fusion IO style thing. Yes, sir.
Is there a way to check the status of the battery?
I'm gonna have a slide on that. Great. Other questions? Yes, sir. Mr. Jim.
Is it common to actually run a Fusion IO underneath some unwritten code? My impression was that typically you put Fusion IO. Here's my Fusion IO.
Okay, so Jim is pointing out something very interesting. He's correct that normally when you're using a Fusion IO, you really don't have a controller card in there. It's really a direct DMA to the card. So this diagram is not completely accurate. Thank you for that. Other questions? Okay, so let's get into the details. So first, write back versus write through caching. You hear this, like people talk about this a lot. You should know the difference. Okay, write through means that when it arrives at the cache, when a write arrives at the cache, it writes through the cache to the drive, to the storage underneath it, and only acknowledges the write after the lower level has acknowledged it to the upper level. Okay? Write back is a case where it acknowledges it as soon as it arrives at the system, as soon as it arrives at that layer. Sometimes that's safe. If there's some type of durable storage specification or ability at that storage layer, it can do write back. Okay? If there's not, for a database, it should do write through. In terms of where you do that, I hate to do this, but I'm going to actually do a demo, like it's working. I will make it bigger. Oh, come on, where am I? Oh, here it is. Sorry. We'll go for 20. Okay. So I'm sorry it's kind of small, but if you go to in Linux, if you look at your hdparm.conf file, this is a Debian system. You're going to see a lot of comments at the top, okay, and like a lot of comments. But when you get down to the bottom, what you can see is exactly what I've specified for my particular storage. Okay. Now I have several Western Digital magnetic disks, and I have one Intel 320 SSD. So what I've done is for the SSD, I have turned the write cache on. That's how the term that they use. We turn the write cache on. And I know I can turn it on because I know that drive has a supercapacitor. That's an Intel 320. I'm going to talk about the specifications for that in a couple of minutes. Okay. The other drives on this system, I've all marked with cache off because those are magnetic. Those caches on those drives are not battery backed. They're not durable, and therefore I can't. I have to write through them. They're still good. They're still useful because again, when reads go to the drive, they're responded to very quickly from the drive. Okay, so they're not useless, but they're not useful. The magnetic disk caches I have here are not useful for doing write backs. Yes, sir.
With your massive write, you can still access back into write and read it out, or is it just a dump a lot of data in which you can write around it?
So is a typical workload a write and a read and a write and a read, or is it really just writes? Most workloads are just going to be writes, and the reason for that is because you have so many caching layers above that, because you've got the drive, you've got the potential memory on the HBA controller card, you have the kernel cache, and then you have the shared buffers. So it's very rare that something would write it to a point where they had written it, and then the upper layers had forgotten about it so quickly that they go and ask for it again, right? So you're kind of right. It doesn't. It has some value, the read cache, but it's not super valuable because again, you're not seeing a lot of read-write kind of traffic there. Great question. Other questions? Okay. So again, you can kind of see the numbers here. If I actually go, if I'm just going to, um, uh, we actually have a tool in Postgres called pgtest-fsync that I wrote. And if I go to my archive drive, which happens to be a magnetic, and I go pgtop contrib pgtest-fsync is on pretty much default install for Postgres. If I just run that, I'm going to get fsync rates, the rate I can store stuff down to my lower storage. Okay, and I'm sorry it's kind of low down here. Let me just pop it up there. But you can see the rates here as being really kind of bad. 74, 73. Really not very impressive. This is how many of these fsyncs I can do per second. Okay, and again, as I showed you before, my HB parm is not using the drive cache, so this is forcing it down. These are very low-end drives. I think they're like 5,400 RPM. So if I do 5,400 divided by 60, yeah, it's like 90 a second. Okay, and we're seeing 74. That's about all I'm going to be able to do there. Okay, again, you would not use 5,400 RPM drives. They're Western Digital green drives. They're used for archive. Okay, in production, you'd use SCSI. You'd have much faster speeds. But again, what are you going to do? 200, 250? Whoopie-doo, right? If I go to my SSD and I run the same thing, hold on, let me go up here a little better. Okay, there we go. 9,000 a second, right? What is that? 100 times. So, in fact, the SSD is so fast. I don't even have a battery on the HBA here. Like there was no need. When I was speccing out the system, I'm like, well, I have the archive stuff, which again I never run a database on. It's just home videos and home pictures, and I got like 60,000 home pictures, right? But again, everything that I'm running in production is going to be on that SSD. I'm already got a huge battery or huge capacitor on the drive. Do I really need another battery in the controller card? Is it really worth? No. I think if I had a whole bunch of drives, I probably would. But in this case, this is not a high performance system. Okay. But you can see these numbers are big. These numbers are 100 times what we saw on the other system, on the other storage system. Okay. Caching layers. We talked about this. The idea you've got an HBA that might have a battery back cache. Then you've got the storage might have a cache. And then again, some devices like the enterprise SAS type devices, they're going to default their storage to write through because they know you need reliability. Okay. Most consumer drives are going to default to write back. So I had to actually, in this case, I was using consumer SATA drives, and I had to go into my HD parm and specifically tell it. But there is an HD parm utility which will tell you if you're really kind of keen on it. I think it's let's see here. I'm going to pick this one. HD parm. I think it's like that maybe. No. Is it? I can't remember what the okay, let's see here. No, so it's not showing me. I'm looking at the SSD. It's not showing me the. Okay, let's see here. Sorry. Yeah, so it's capital W. Like I should have guessed that, right? So if I look at my SSD, the caching is on. If I look at my magnetic caching's off. Yes, sir.
I'm just curious. Do enabling write cache on a magnetic drive will give you any performance benefit?
So will enabling a write So will making a drive write back on a magnetic disk, will that give you a benefit? Is that the question?
Yeah. You just showed the configuration for easy farm here, and
Yeah.
if
If I
go on and run the same.
Yeah, okay, totally. So that's the question. If I changed this HD PARM for the magnetic drive and ran the test again, would my numbers be different? You bet they're going to be different. They're going to be a lot different, right? I'm going to now get thousands of writes because again, the hardware, and if we have time, I'll do it at the end. But the hardware effectively is going to say, okay, you want that drive cache to be right back, then I'm just going to acknowledge it as soon as it gets to the cache, and oh boy, it's going to run really fast, right? I'm probably going to get very similar numbers between the two servers all of a sudden. The SSD and the other are going to be pretty much the same. Now, if I lose power, I'm going to corrupt my database, but it would work, and I would get that, and somebody might turn it off to do a bulk load or something like that. You could, yeah. There's some other settings in Postgres that actually will reduce the requirement for fsync. So I'm showing you the default configuration where Postgres is going to require that fsync to happen every time. But if you turn synchronous commit off in Postgres, then effectively it will not wait for the acknowledgement, and therefore it won't corrupt your database, but you might lose a couple transactions. So Postgres has some abilities to sort of reduce these durability requirements for particular sessions, for particular tables if you want to. I'm just showing you the default because that's the way most people run. And again, you would probably not want to do it all the time, but you can do it in certain cases if you wanted to not do that. It would be easier to do that than to actually touch the drive and change the parameter live. Yes. I'm sorry, question back here. You're good. Okay. Again, the HBA is you can actually go into it and control the caching mode. It knows if there's a battery there or not. For magnetic disk, just some tips here. More disks that are small are better than a lot of big disks. Because again, you can do a lot more concurrent stuff to multiple smaller drives. Obviously, bigger drives are going to be a bigger bottleneck. RAID 5.6 is too slow for database writes. Not a huge big deal if you're doing read-only, but if you're doing writes and you care about performance, RAID 5.6 is really not the way to go. Question over here, sir. Nope. No, you're good. Okay. The other question, RAID 10. RAID 10 is what people normally will use for databases because effectively it doesn't have – the problem with RAID 5 and 6 is every time you do a write, you have to hit like 3 devices. And you have to wait for all 3 devices to durably store, right? So it's like not only waiting for one drive to spin, we're waiting for 3 drives to spin. Okay? Again, not a whole RAID 5.6 is fine if you're doing like sort of non-storage of like documents and stuff where you're not waiting for fsync to come back, right? But when you're doing a database where you do care about fsync, really that RAID 5.6 is not the way to go. RAID 10 is normally what people will use. SCSI disks normally are designed for enterprise workloads. SATA and not as much, although this is changing somewhat. But just be aware when you buy something, if you're buying something that's like designed for enterprise use, designed to be on 24 hours a day, designed for like vibration and heat that you get in these cabinets that have like dozens of drives all spinning. The bottom line is that consumer drives are really designed to hit a price point. So that, like people are going to go into Amazon and say, how much is a 1 terabyte, 2 terabyte drive? And they're going to look at prices, and the majority of consumers are just going to buy whatever the cheapest one is, right? When you're talking about enterprise use, you have to be a lot more careful because, again, your downtime is much more expensive than it is for an ordinary consumer. The URL there at the bottom goes into some detail about how how enterprise drives are slightly differently constructed. By the way, if you're wondering about this presentation, it actually is right here. If you ever want to look at it, you can actually download it. So that URL at the bottom there is actually the presentation. I should have mentioned that at the beginning. There's actually 30 presentations at that URL, or 40, something like that. So again, if you're ever curious to look this up again, that's where you would do it. So Again, it's really kind of hard to figure out what an enterprise drive is and whether it's more reliable or less reliable. There's been a lot of studies. A lot of the studies concluded that enterprise and consumer drives have the same reliability. I don't. I guess so. All I'm saying is, when you're doing a database, you probably want to look for quality first. Price is probably not the single driver. I have had cases where vendors will really take out features that a database really needs to, like, save $200 on a server, and that's really not the vendor you want. I don't know how to put it, but just make sure you get something that's got what you need. SSDs. Again, I talked a little bit earlier about the fact that SSDs are a little different in terms of how they handle databases. The SSD effectively has that cache that we talked about is really a staging area. It's kind of a weird concept, but SSDs really only write their data in 128K chunks. So unlike a magnetic disk, which is roughly 512 bytes in length, SSDs have a really big block size, like 128K. So the reason that you have to use that staging area is if somebody's writing 8K, 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 if you have to put each 8K onto the SSD, you've got to read the 128K block in, add the 8K, and write it back again. And you're doing that over and over again. The way normal SSDs work is you write the 8K, it goes into the staging area. Because there's a supercapacitor there, the write's acknowledged right away. Frankly, even if there isn't a supercapacitor there, most drives will acknowledge the write right away, which is bad for databases. And then effectively, at some later point, it will coalesce the writes as the staging area gets more full. It will coalesce the writes and then read in that 128K, write it, and then put it back onto the flash. Okay. So again, that whole concept of how the writes happen on SSD is quite a bit different. Yes, sir. So, yeah, is there a maximum amount of writes that an SSD has? Yes, there is. The number is pretty high. It's much higher than people think. Normally, if people are running SSDs, you should be running a utility which monitors the health of the SSD. On Linux, it's called SMART, S-M-A-R-T. So there's a SMART protocol for drives, which allows the operating system to probe into the drive and learn the health of the SSD. The wear level is what the term is, the wear level of the SSD. You can run diagnostics on the drive. You can see how many errors that drive has had, the temperature of the drive. There's a whole bunch of things you can do. So if you're using any database, any server, you should definitely be running some type of smart monitoring on that system, because normally before a drive dies, you're going to get some kind of warning. Smart's going to give some kind of warning to say, hey, something really weird is happening here. So in Linux, it's called Smart CTL. So I can actually run, Smart. Let's see here. I can do, pick that drive right there. I can say Smart CTL-A, and I can give it a drive. And effectively, it's basically giving me this information about the drive, the mode it's in, and then down here, here's all my stats of how the drive is doing. And in fact, there's a media wear out indicator right there, which identifies that this drive is 97% good. So that it's been here for 3 years. I've used 3% of the drive. Okay. And again, as that number gets low, you'll get an email saying, but again, this is not unique to just SSDs. Anybody who's doing any kind of storage, you should be getting reports if there's anything unusual about the Smart. Again, you can run your own diagnostics as well. Good question. Other questions? Yes, sir. So so the question is, if there's a power loss, is there some kind of way the SSD will sort of power down or save the data? Right. Super. It has a supercapacitor. So how does it work? I believe the way. I don't know exactly how they do it. Whether there's two ways of doing it. One is to effectively use the battery to completely write any dirty data from the cache into the SSD, into the flash chips. Okay. A second simpler way is to have a little bit of flash extra on the drive, and when you lose power, you just take what's in the cache and you write it directly to that storage that's reserved just to hold the staging area. Then when you power back, the first thing it does is it brings the staging area back, and then it continues to power down. Which one it does, I don't know. I do know we've actually done a lot of electric power pull tests on these. In fact, the Postgres documentation actually references a specific pull test, which I think is really cool, where you have one computer writing to another over and over again, and then you pull the power on the other computer and you plug it back in again. Then the first one will tell you if all the data that it said was written had been written, and that's like electric pull test. Rather than just pulling it out and see if the database is corrupt and putting it back in again and trying it over and over again, this tool mentioned in the docs. I'm trying to remember the name of the tool. I can't remember the name. I know I put it in the docs, but I can't remember what it was. But anyway, effectively, you run the tool against the drive, and then if there's any a loss, you're going to know it right away, because it just hammers the thing, and it keeps a record of exactly where it stopped. So it says, I was at byte 4,000 when I stopped getting acceptances. So then it basically starts up again, and it goes and says, okay, do you have byte 4,000 for me? And if it doesn't, that drive has failed. Yeah. Great question. When would you use SSDs for? Oh, I'm sorry. Yes, sir. So the question is, when an SSD fails, is it catastrophic, or is there some read-only mode? Normally, when an SSD fails, it's completely inaccessible. It's bricked. So I've not heard of any case where it sort of degrades. Although I will say that if you're running the smart tools, you'll get a warning usually before it dies, and then you pull everything off. But usually when it dies, like there's no like I can get in there and still get stuff out. No, it's usually just gone. So you're saying it doesn't look like it wears out. It doesn't. It looks like something else is going on. It depends. You're right, because you can get SSD failures before the wear out interval. So just because I got 97% doesn't mean that thing's going to take a bullet tomorrow, right? And there's a whole bunch of ways an SSD can die, by firmware bugs, by lightning. There's a whole bunch of ways it can die even before the wear out. I guess what I'm saying is when that wear out gets to 0, when I'm going from 97 to 0, I'm going to swap out that drive. Like, I'm not going to wait around for it to die. But effectively, I think the way they design them is if you replace it when it gets to 0, the wear out is not going to kill you. Probably something else is going to kill you. But it could be anything. Yes, sir. Yeah. So is that wear out number sort of like is there some kind of reserve space out there that you're measuring? I don't think they have really a very good number of exactly what the wear level is. Flash chips, by definition, are not something that can be perpetually written to. So you're always going to have a limit to how much writes you can do to it, and that's a known fact. The question is, how much is it that? And effectively for enterprise drives, they're going to basically say, we're going to just cap it at 1/10 of the writes. And we're just going to, it doesn't actually go and like look to see, oh, are these little, atoms starting to wear out, I think. I think it basically just calculates the writes and then just says, oh, I think I'm near thing. It's time to throw this thing away. Yeah. Yeah. Yeah, there's always extra flash in there, yeah. Oh, I see.
does that number denote the one, or does that actually go into that storage space?
So
So is my drive degrading
the
storage
question is, when it says 97%, does that mean 3% has gone bad so far? And no, it doesn't mean that. It just means we've got a little meter on there, and we think it's going to be fine until it gets to zero. But there's no. You're right. It's going to do wear leveling. It's going to move stuff all around. If there's bad chips in there, it's going to hopefully tell me with smart, but it's also going to map around those. We've had very good experience with the enterprise quality SSDs. We had terrible experience with the consumer ones, which was quite disappointing. Yes, sir. You had a question in the blue shirt. Nope.
Oh, I was going to say, back to the catastrophic failure, if the wear level isn't a good indicator of how long the drive life lasts, you can still face some catastrophic failure. Is there any kind of warning or any kind of, do you get any kind of indication that the whole thing is about to go?
So you get any indication that something's about to go, and effectively that's what that smart CTL utility will do. Is that any diagnostics coming out of that drive, the smart CTL will run a dump of the basically health of the drive every couple hours, and anything that changes, it'll send an email to the administrator. Yeah.
The way that flash NAND memory works is there's cells, you can write to the cell, but you can only write to it so many times. So in a sense, as you write to the drive, you're consuming the drive. So that, I think, is what the 97% indicator is. Oh, you've used up, 97%, you've used up 3% of the life of the drive. That they can kind of measure. They know, okay, this is how many times you can write. The other thing that can happen, though, is that, let's say copper gray, whatever, and the thing just goes, whoop, and that's a lot harder to actually predict. So there's two distinct failures.
Good. Good. Some little stuff for database specific and SSDs. The SSDs are really good for things you have to do durably, like the write-ahead log in Postgres, or I'm sure other databases have a similar thing. So that's a great thing to put on the SSD. Another thing is random I/O. Random I/O is terrible for magnetic drives. It's got to move the head around and wait for the thing to spin around. That's really good for an SSD. Sequential speed, SSD versus magnetic, it's kind of the same. Now, I'm not saying it's like exactly the same, but they're in the same ballpark. Whereas, as you saw, the F-Sync was 100 times different between the magnetic and the SSD. Okay? Sequential, it's not 100 times. I'll tell you that right now. It's probably not even 10 times. So my point is that if you only have a limited amount of SSD, put the write-ahead log in there and try and put your indexes on there, because that's where you're going to get the biggest benefit. Now, you're still going to be randomly going into your data files from the index, so there is, again, some value to having those on SSDs as well. But again, random I/O is really where the win is for an SSD. I talked about some of the changes we thought we needed to make for SSDs. It was going to revolutionize everything. Well, not really. The only real change we had to make in Postgres was the idea that we have an optimizer cost for random I/O. By default, it's 4, so we assume random I/O is 4 times more expensive, but then there's a whole bunch of caching effects I'm not going to get into. But effectively, the big change, which took 20 lines of code, was to allow you to set different random page costs on SSDs or different table spaces. That has been really the only change the Cord server has had to make for SSDs, because now you have some storage, some table spaces which have very good random I/O characteristics, and some that may have very poor random I/O, and we needed a way to tell the optimizer that. But in terms of sort of revolutionizing everything, we're waiting. We don't see it. Another thing you can do for SSDs, because again, you're writing to a cache, you're not writing to a physical drive. Effective I/O concurrency, that's another Postgresism, where it basically says how many concurrent I/O operations can I have to a single device. Effectively, you can set that super high for Postgres now on an SSD, because again, you're writing to a cache which can absorb much more I/O activity. The actual drive I have is an Intel 320. That actually has been superseded now. There's a 330 now. There's a 720. That drive, again, is 2 or 3 years old. But if you look at that URL there, it kind of goes over why that supercapacitor is so important, and sort of talks about the use of enterprise drives in database work and why that's kind of important. So they're just sort of a reference for you. File system options, again, not really related to storage, but we would rather use XFS or ext4 rather than ext3. ext3 has very poor fsync characteristics we found. You can reduce things like file system logging, particularly for the xlog directory. You could disable A-time. Again, just some ideas that you might want to look at. I'm sorry? ZFS? ZFS? Yeah, a lot of people like ZFS too. I'm sorry, I didn't mention it there. Yes, sir. So the difference in terms of A-time, like, should you turn it off completely or rel A-time? I have to admit I've never done any actual experiment with that, so I can't specifically say. Thank you. Battery back unit, we've talked about this a lot. Just to sort of summarize what it is, it's basically either a battery or a supercapacitor that you can normally visually see on the device. Older units would only be good for like 2 or 3 days. Newer units have a much better facility. They use the option I told you where usually they have a flash on there, and they just take the cache and they write it to the flash and they just shut down. But this is an older system, and again, I'm just in case that's an issue for you. Again, some of them write back to the local flash on power failure. Again, it will normally detect the battery or the supercapacitor there. It does require some monitoring, so you should, as an administrator, get a message when it looks like the battery. Because what would happen in the old systems is when the battery died, it would all of a sudden change the cache from write back to write through, and all of a sudden, for one of a couple batteries, your system performance has gone down 100 times. And you know that you do not want the boss walking in and asking, why are we so slow? And he's like, well, we don't have any batteries here, right? So a lot of the joke was, like, if you buy one of these things, like, buy some extra batteries so you're ready in that kind of case. This is actually an older card, but just give you an idea of what it would look like. So this is a Adaptec controller card. This is the battery right here, and in fact, there's a blow-up. In fact, it says Malaysia lithium-ion battery right there, okay? There's the wire. I think this is the little beeper that goes off when the battery goes bad, so sometimes you may not hear the battery if it's in a big room. So again, think of your failure cases. Again, most of the systems are using supercapacitors and flash now. You don't see as many physical batteries. Kind of to wrap up, just some sort of general things that I get asked. Shared storage. Shared storage is fine. A lot of people love it. It's really easy to administer and so forth. But it's shared, okay? And if you know anything about databases, they don't like to share. Because when they do a write, or particularly an fsync write, it's got to wait for an acknowledgement. So normal systems, when they write, they just go, I wrote it, and then I'm just going to write to the kernel, and the kernel will deal with it later. But if you're doing things that actually require acknowledgement, are going to wait for that acknowledgement, then your shared storage can be a bottleneck. So just be aware of that. I know it's easier for management. I know it's easier for resource management and so forth. Just be aware that that can be an issue. Okay. I've talked all about storage, but and this is the triangle, right? Spent 59 minutes talking about storage. Now I'm going to talk about memory. Obviously, memory is useful. It's important. The more memory, the better. Databases love memory because the more memory you have, the fewer reads you have to do. Doesn't help a lot for writes, but for reads, it's really useful. If you're lucky, you can get enough RAM, so like 5 minutes of your working set is in RAM. So then all of a sudden you're not pulling stuff in and throwing it out and rereading stuff in short periods of time. You should be monitoring the failure of your RAM. I know a lot of consumer servers, they don't have any real memory detection. For an enterprise server, there should be memory detection. There should be ECC RAM. If you get a memory error, you should get a message about that. Okay? Usually it'll cause the process to crash, and therefore you have some bad RAM in the system. Make sure you have a system where you're getting those messages if there is bad RAM, because no matter how good your RAM is, the more RAM you have, the more likely it's going to fail. Cosmic radiation can cause RAM problems. Just make sure you're on top of that, because as soon as the RAM isn't reliable and it starts corrupting your data really is corrupt and your database becomes corrupt, and you don't want to go there. CPUs, this is the final thing, right? It ended up at the CPU, right? Finally. A lot of databases do allow parallel operation of CPU, like they allow multiple CPUs to be used for a single session. Postgres does not currently support that, but we are working on it. So I think 9.5 will have a limited capability of parallel query, which is what is normally called the industry, and that will be improved in 9.6 and 9.7. If you're using a lot of server-side functions, you might want to invest in bigger CPUs, particularly something like PostgIS or very numeric, complex computations. You might find CPUs an issue. The only other time you're really going to find CPUs an issue is if you are doing a mostly read-only workload and all your data fits in RAM. So, there's no I/O because everything's in RAM, okay? And all of a sudden, your system really is running as fast as those CPUs are. So if you find yourself CPU constrained, that's a win, okay? For a database, that's a win, which means you have enough RAM, you have a sufficient I/O channel that you're now choked on the CPU. You might need to get bigger CPUs and more CPUs, but the idea is that is a win because you have done everything you need to do at the lower levels. So now the system is only bottlenecked by how quickly you can do it. What you don't want to do is the opposite, buy a lot of expensive CPUs and not spend the money at those lower levels. So, in summary, compatibility is not the same as capability. Those two cars both have steering wheels, they both have gas pedals. They're not the same. So, when you're purchasing stuff, when you're speccing things out, remember this triangle, remember how that kind of fits, okay? Put the money where you're going to get the benefit, and then only worry about that upper layer when you've decided that you have a sufficient throughput at those lower levels. Okay? Yes, sir. Right. So the question is, he's using magnetic disk. He has a battery backup on his controller card. How does that eventually, if he loses power, how does it eventually get written? The HBA actually has an operating system running on it. So when it detects the power's lost, it'll typically take what's in the cache and write it into like a flash storage. And then again, when it starts up again, it'll read the flash storage back and then make sure it gets down. So technically, when you lose power, the data isn't on the drives yet, because the drives have died because they have no power. But again, by the time you actually start up again and you actually can access the drives, that HBA will have already flushed everything down. Okay? Yes, sir. This will be the last question. Yes? So the question is, with improvements in write-ahead log performance for Postgres, is there an additional need or additional emphasis now on SSDs? I wouldn't say additional. I think 100 to 1 kind of speaks for itself. I know we've gotten a little faster, but we haven't gotten 100 times faster, right? There's always been a night and day capability between battery back storage and non-battery back storage. So I don't think that the calculation of when you should use something has changed. I do think that with SSDs, it's not as important to have a battery on the controller card because, again, now you have the battery kind of spread out. So thank you very much. It is 4:04. I will be here if you have any questions. I guess it cooled off a little bit in here, so I'm feeling a little better. And I always love this conference, so I hope you enjoyed as well. Thanks.